So we're going to solve this differential equation, and this is the initial condition. Now, let's say suppose the Taylor series of y is equal to is equal to this, according to the Taylor theorem. Of course, we assume that y is differentiable for all the derivatives. Now, the reason that we expand y at the center 0 because it's pretty much because the initial condition y is defined as 0. We assume that it's going to be defined at all the derivatives at 0. So now with that, so this is the first step. We write the Taylor expansion for y. Obviously, if we want to solve for figure out what y is, we must know all these constants: y prime 0, y double prime 0, y third derivative at 0, and so on and so forth. So in other words, we do need to know y of 0, which is given, but we also need to know y prime 0, y double prime 0, all the derivatives at 0, so that we know what this power series is, and then we can use what we learned to find the function representation for this power series. So that's what we want to do. Now, step number 2 is look at this guy. We're gonna differentiate this this equation with respect to t again. So we're gonna do that. When we find the derivative, y prime becomes y double prime, right? Minus. And here, 3 times yt, when you find the derivative, it becomes 3 times y prime t equals 0. So this is true. And then, first of all, we do know that from the given differential equation, when t is equal to 0, we do know y prime at 0 minus 3y of 0 is equal to 0. And then here we do know that the y prime 0 is equal to 3 times y0, which is 3 times 2 and equals 6. So this is something we can find immediately using the initial condition and the original differential equation. So now we need to use that to find y double prime at 0, because when we plug in t equals 0, y double prime 0 is going to be 3 times y prime of 0, which is 3 times the previous one, which is right here. 3 times 2, which is 3 squared times 2, right? Okay, so this is what we know. And therefore, you just differentiate again. So you're going to get y third derivative t equals 3 times y double prime t, and which we can use it to find y triple prime at 0, which is 3 times y double prime at 0. And y double prime at 0 is right here, which is 3 squared times 2, so which is 3 cubed times 2. So obviously, you can now kind of look at the pattern right here, right? So when this is third derivative, this power is 3. When this is second derivative, this power is 2. When it's first derivative, its power is 1. So with that, we can... So therefore, when you say y the kth derivative at 0, you know it's going to be 3 to the k times 2. So with that, now this power series representation can now be written as y of t equals, so what is the y0, which is 2, plus what is y prime 0, which is 3 times 2 times t, right? And then what is y second derivative at 0, which is 3 squared times 2 over 2 factorial t squared, and so on and so forth. So let's write a few terms. So the next term must be 3 to the power 4 times 2 over 4 factorial t to the 4th plus, and so on and so forth. Now, one thing that I do see is the 2 is really just a constant for any of those. So I can actually factor out these 2. So let's do the factor out these 2. And you're left with 1 plus 3t plus 3 squared t squared over 2 factorial plus 3 cubed t cubed. Now I hope that you're comfortable with me factoring out move the power out. Okay, so similarly I can actually here I can actually do that, right? And you probably now know where I am going to. So the next one is 3t to the power 4 over 4 factorial, and so on and so forth. Now you need to recognize, so like I said, you need to be able to recognize this structure, right? So think of 3t as your the variable in the box. So therefore this is actually 2 times, and now you should be able to recognize this is just e to the 3t. So therefore you do see that this is the solution for the differential equation. So this is it.